In this video, we are going to be covering function composition. The definition of function composition is basically putting one function into another in where the variable places are, or where the variables are of the other function. There are two ways that you can also see this happen, notation-wise. So the first is you might have kind of this open circle here. It kind of looks like multiplication, but it's different because it's kind of not filled in at all. And then you kind of see it like f of g of x is how you'd read that. And then you might see it with the g on the inside, the f on the outside, or you could flip them both around and have the g and then f and x. And that's when you have f in the inside and g on the outside. And so we're going to look at two examples here where you are going to be kind of inputting them into each other. So we're going to look at, well, first, if g is on the inside and f is on the outside, and then vice versa. And then we're going to look at the domain of each composite function as well. So for starters, part A, we're going to look at f of g of x. So we have g of x, and then g of x can put into f. So how we're going to kind of start off is, well, I need to basically put 4x plus 1, which is our g value, right? Our g function right here. That is going into to f. So you can see where f had an x, well, we put 4x plus 1 where both the x's were. And then the plus 4 didn't have a variable, so it didn't change. So if you square 4x plus 1 multiplied by itself, we're basically doing 4x plus 1 times 4x plus 1. That is what equals 16x squared plus 8x plus 1. And then this minus sign is going to be going into each of those two parts, and that's what gives you minus 4x minus 1. And then the plus 4 is left over. And then lastly, we got to multiply it by 2 into each part here, so 2 times each one of those three terms. And that gives you this 32x squared plus 16x plus 2. And then we have a minus 4x plus 3. And then finally, our answer is this right here. So that equals f of g of x. And remember that you're kind of using the g is on the inside and the f is on the outside. So g, and as a function by itself, the domain of that function is just all real numbers at the line. Lines go forever in both directions. And so that would mean that the composite, if all of your inputs are all real numbers, the domain of the one you're putting it into would then be all real numbers as well, since that's what you're using, the inputs. Your g is your inputs of your composite. And that covers our first example. Our second example, we have here. So we're using the same two functions, but now we're kind of reversing it for part B. So now we have f is our function that we're going to be putting into g, and that's what this arrow is kind of showing you right there. And this one's a little bit quicker, and so we can kind of approach it in, well, I'm doing 4 times what g was right here, and that gives me 8x squared minus 4x plus 16. With the plus 1 in the end not being affected. So all you'd have to do is just put together the 16 and the 1 to get our answer right there. And that would be equal to g of f of x. And remember, that's the same thing as g of f of x, where f is on the inside, g is on the outside. If you think about the domain of this composite function, our f function became our inputs. Well, this is a parabola. Parabolas have the domain of all real numbers, so that means that the composite function also has a domain of all real numbers. Those are about 2 examples, so let's walk through a few together. So for starters, we have in problem number 1, 2 linear functions. So f of g of n is what we were looking for using these two. So what we are basically going to be doing this is the same thing as f of g of n. And so we're going to take this purple one, 2n. So that is going to be where our variable is. So it's going to be 2n in parentheses. And then we're going to be putting that into, oh no, we have that a little reversed. So let's back up a second. So we have our g is on the inside. So our g is going to be going into 2n. And so let's do that in red here. So we have negative 2n minus 4 is our g, and that's on the inside. And then in purple, we just have a 2. 2 times n, where our n is right there. And so 2 times negative n minus 4 would be negative 2n minus 8. Both of these are linear functions. Since our input is g of n, that's a linear function as well. And since that has a domain of all real numbers like before, we can say that that applies here as well. Moving on to number 2. So we'll use colors again. So blue for G and red for H. So you can see that this means that we're going to be doing G of H of N. So our H is going to be our input. So we have our N minus 1 that we're going to be using as our kind of N value. And so our G on the outside, we have a 2, and then a plus 3 outside of it. And so if you multiply that all out, you would have 2n minus 2 plus 3, or as a final answer, 2n plus 1. And since this is all again linear, we know our domain is automatically kind of all real numbers. All right, number 3 in this video here, we have h of x and g of x. So first, well, h of g of x, that is the same thing as h of g of x, like so. And so our g in blue is going to be on the inside. And so that means we can write 4x plus 1 on the inside. And then in red, we're going to kind of add in the stuff that's outside of the variable, like the squared and the minus 2. So now we just need to multiply this all out. So we would just be doing 4x plus 1 times 4x plus 1. And that minus 2 is going to be the end. If we multiply that parentheses out, we would have 16x squared plus 8x plus 1, and then a minus 2 left over. So the 1 and the minus 2 would combine, and we would get 16x squared plus 8x minus 1. And that equals h of g of x. To finish this video, we are going to be looking at how we can evaluate composite functions, which is actually an easier process than what we just finished doing. So now if I'm going to do f of g of negative 2, basically I'm going to enter in negative 2 into g, get an answer, and then use that answer to put into f. So first I would do g of negative 2. That would be negative 3 times 2 plus 1. And negative 6 plus 1 equals negative 5. And that negative 5 is what I'm going to put into f, since that's on the outside. So I'm going to do f of negative 5. And I would just be doing 2 times negative 5 minus 7, which would be negative 10 minus 7, making it negative 17. And then moving to part B, our last problem of our video, let's kind of quickly, we basically just did f of g of negative 2 as our answer there. Let's just kind of wrap up that. So for part B, we need to do f of negative 1 first. So that means I got to do 2 times negative 1 minus 7, which that means that f of negative 1 would be negative 2 minus 7 equaling negative 9. And then we can take that negative 9 and put that into g, and we can figure out that g of negative 9 would be negative 3 times negative 9, and we would be adding 1 to that. So g of negative 9 now equals 27 plus 1, which is 28. And we just found that 28 is equal to g of f of negative 1. And that concludes our last problem of this lesson and concludes both function composition and part 1 function operations. Thank you for watching.